listening to section 2.1 of Calc 11. We're going to talk about something called angles in standard position. You're thinking, what does that mean? Well, I'm here to tell you. So, what we want to do is find a way to standardize how we talk about angles. And what we've done is we've been able to create angles and draw them on a coordinate system. Now to do so, we use two rays, and of course rays are just, I guess, these lines like this, but there's an arrow only at one end. So we use two rays with a common endpoint, that's right here, to show the angle. So to do so, we want to begin our ray at the positive side of the x-axis. So when we're drawing angles in standard position, always start here. And then we're going to rotate our ray. You're going to do it counterclockwise. If you're drawing a positive angle, so you're going this way. Whoop. Okay, so there's my angle. And if we're trying to do a negative one, yep, you guessed it, clockwise. And notice the positive side of the x-axis, that's over here, is called the initial arm. And the other ray, the one that rotates around the origin, is called the terminal arm. So over here, terminal arm. Alright, so knowing these things now, let us talk about what an angle in standard position actually is. It's the angle that is created between the initial arm and the terminal arm. And the vertex is always located at the origin. And the angle that's created is referred to as theta. And we use this little symbol theta that you hopefully have seen from grade 10. As a quick review, let's just tell you where the quadrants are. So hopefully you understand this is quadrant 1. And that's always, in this case, starting at 0 degrees. And if I rotate counterclockwise there, it goes from 0 to 90. Quadrant 2, yeah, 90 to 180. Quadrant 3, that's down here, so from 180 to 270. And last but not least, quadrant 4, going from 270 to 360, or of course you can call that 0 degrees again. Okay, so knowing quadrants and all this, now let's try to draw some angles in standard position. Here's a few examples. I'll do maybe the first two of them, and maybe you can try the next 4. So 70 degrees. Once again, we start by always drawing our initial arm. And then we'll rotate, in this case, because it's a positive angle, we'll rotate counterclockwise. I don't want to go too far to the right angle, because that's 90 degrees, so I'll just stop right about there. And I'll call this angle here 70 degrees. Once again, it's just a sketch, so we don't have a protractor or whatnot, but do a good enough sketch that we can understand you're correct. 210 is the one for B. Once again, start at the initial arm, and let's rotate 90, 180, and let's go just a little bit more. Oh yeah, looking good. Theta in this case is 210. Okay, I've shown you 2 examples. It's time for you to try the next few on your own. So please pause the video, go ahead and try them, and when you're done, press play and let's check your answers. Interesting. It's a negative angle, so we start by rotating this clockwise. So here's what happens. Clockwise, 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 clockwise. That's negative 90. Clockwise, 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 clockwise. That's negative 180. So I need another about 20 more degrees. And there you go. This is the angle, negative 200. And for F, this is 520. Whoa. Okay, let's take a look as I go around. 90, 180, 270, 360. I need to go more, right? So another 90, 360 plus 90, that's 450. 450 plus 90 is 540. Whoa, 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 that's too much. So I must pretty much just kind of stop right here. Notice in this case I've gone around like at least once, and that's perfectly fine. But this is how I show 520 degrees. Cool. Did you get them all right? Give yourself a pat on the back. All right, turn the page. Wait, let's not turn the page. Let me just put that right here. So in example 1D and F, or D, E, and F, those are the ones that you see now on my screen. Here they are once again. What do you notice about those angles in standard position? I hope you can see that the terminal arm seems to be in the same location, same position. That means that the angles of 160 degrees, also negative 200, and 520 are what we call coterminal. Co is like sharing, so they share the same terminal arm. So we call these coterminal angles. Now here's a question I have for you. If I give an angle in standard position, how do we find other coterminal angles? So given the 160, how can I find the negative 200? Or how can I find the 520? Or how can I find all the other ones? If you're thinking, going around the circle once is 360 degrees, that's a good start. Yeah, all we need to do is just add or subtract. Now, if you just wrote down 360, that's perfectly fine. But remember, I don't have to go around just once. I can go around twice, 3 times, 4 times, 5 times, 6 times, 7 times. I can go around a whole bunch of times. So because of that, I will say add or subtract, and I'll put in these keywords, multiples of 360 degrees. And that is a better way of defining what a coterminal angle will be. Okay? All right. One more definition here, and then we'll be able to tackle some additional questions. So another thing you need to understand, and this is very important for our next section of studies and for Math 12, so make sure you know this stuff about reference angle really well. The reference angle of theta, that is the acute. So if you don't remember acute, that means it has to be between 0 and 90 degrees. So it's an acute angle between the terminal arm, and this is the key part, and either the positive or negative side of the x-axis. And this is called the reference angle. We denote this as theta r. In addition to this, you'll see something called the reference triangle, which really is the acute triangle that contains the reference angle. And once again, one of the legs of the triangle must be on the x-axis. So once again, let me try to draw a few of them for you here, and I'll let you practice again. So it says, draw the following angles in standard position. That you should know how to do. Then identify the reference angle. That will be new. And then using a different color, sketching the reference triangle. That is also new. So 135 degrees. Let's draw the angle in standard position first. We'll start always on the positive side of the x-axis, and we'll rotate counterclockwise 90, about here. So I would say this is my angle 135 degrees. Now, which or where is my reference angle? Once again, the reference angle by definition is an acute angle between the terminal arm, so here's my terminal arm, and either the positive or negative side of the x-axis. And so in this case, in order for me to create an acute angle, I'm going to have to use the negative side of the x-axis. And yes, this angle in here, that's my theta r. Okay. By the way, if you're curious what my reference angle measurement will be, I think theta r in this case would be 180 minus 135, so 45 degrees. And my reference triangle, I'll just highlight here, will be this one right there. Okay, there's my reference triangle. Okay, 60 degrees is the next one, so let's try to draw this. 60 is right about there. Here's my angle theta. Notice in this case I'm also asking you for the reference angle, so once again here's the terminal arm. Where's the positive or negative side of the x-axis? I think it's this side. And you're saying, whoa, 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 stop right there. Isn't it the same angle? The answer is, you bet. So theta r, in this case, is also equal to 60. It is also the exact same angle. And once again, my triangle is like here. Okay. Whew. I've shown you two. Guess what? You do the next 4. And by the way, this should be C, D, E, and F. All right, go to it. Triangle always has to use the x-axis as one of its legs. Do your diagrams look like mine? I sincerely hope so. If so, let's move on. If not, you make your changes. But if you were curious how I found the reference angle measurement so quickly, I'd like us to take a look at a few examples here, and maybe you can find relationships between theta and theta r. So our first one, let's assume what happens is the angle theta is in the first quadrant. Okay, so this is quadrant number 1, right? Quadrant number 1. So what happens in this case? What is the reference angle? Well, the reference angle is the same thing. So theta r is equal to the angle theta in quadrant 1. We're going to do them all. So quadrant 2 is over here. Here's my angle theta. Where's theta r? You guessed it. It's over here. Now, what's the relationship between these two? Well, notice that the two angles added together will give you a straight line, which is 180 degrees. So if I want to find theta r, that'll be just 180 degrees minus our actual angle theta. And this is true when it's in quadrant 2. Quadrant 3 is next. So once again, I'll quickly draw an angle here, theta. Where is theta r, or the reference angle? Yep, it's right here. And how do we calculate theta r in this case? Well, theta r seems to be larger than 180 degrees. It's like a little bit of extra. So in this case, theta r will be the angle theta, because that's more than 180, subtract 180 degrees. So notice quadrant 2 and quadrant 3 almost the same, but you have to reverse the order of the subtraction. And quadrant 4 is the last one. So that's way over here. Whee! And theta r seems to be over here. Notice in this case, if you add theta and theta r, you get one complete rotation, and that's 360 degrees. So if I take 360, subtract angle theta, you'll find theta r. Now, ladies and gents, do I want you to memorize this? Not really. I'd rather have you understand it. But if you can't understand it, then yeah, this would be something that I would definitely have you memorize, because this will come in handy once again in section 2.2 and also in math 12. All right, we're halfway there. Let's turn the page. Why don't you try example 3, okay? Because I think you can do this on your own. So, once again, you read the question, you do the drawings, and double check your answers with mine. So 25 is here, and if I reflect this in the y-axis, I think the answer is over here. And what would this measure be? Well, this would be 25, so 180 take away 25, I think that's 155 degrees. The x-axis, so let's get here's 25, and the reflection would be down here. You're looking at this angle then. Well, this is also 25, so that's 360 minus 25. How about 335? And finally, you're doing both the x and the y-axis, so let me do the y-axis one first. And we'll reflect that to the x-axis. And so ultimately, this is 25. This is my angle theta. In this case, it's 180 plus 25, 205 degrees. Alright, so that was just some practice doing reflections and trying to figure out the angles in standard position. Notice the 25 actually was my reference angle in both quadrants 2 and 3 and 4. Alright, here's a little bit just for those of you doing physics. For those of you taking physics, let's just quickly mention that directions are also defined as measures either east or west from north or south. You're like, what? What does that mean? So let me explain. If they give you a direction expressed this way, n, which of course stands for north, 35 degrees west, that means to draw the angle, you start from north and measure 35 degrees towards the west. So what do I mean by that? Here we go. Start from north, measure 35 degrees to the west. So this angle here is 35. Now, we're not really interested in describing angles like that. We're interested in more the standard position. So let me just add a comma here and say the standard position, and please write this in your notes, measure for n 35 degrees W is, can someone tell me? Once again, you're saying let's start from the initial arm on the positive side of the x-axis, rotate this way, whoop, that would be 90 plus 35. So yeah, 125 degrees. That is the actual standard position angle. Okay. So, knowing that, I think you can try example 4. I'll do the first one with you again, and hopefully you can try B and C on your own. North. We'll start north. This time we'll head east. east, 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 80 degrees. Whoa, that's far. So there's your angle, N80 east. The standard position angle is just this one here. And I think that's 90 minus 80, or just 10 degrees. Okay? Okay, you try the next. South, 40 to the west. That's 40 degrees. Ooh, what's that? Theta in this case would be 270 minus 40, or 230 degrees. And this one here, south 15 east. Let's go 15 degrees to the right. My standard position angle, 270 plus 15. How about 200? Oops, 85 degrees. Cool. Alright, just some quick notes about special triangles. You'll see this again in section 2.2. Very, very important. There are two of them you should know by heart. If you had me in Math 10, I taught them to you. But if you didn't, let me quickly tell you now. They are useful, very, very useful in future math studies, and you'll still need them in university calculus for sure. Okay? Remember that phrase, SOHCAHTOA? Remember that stuff about a triangle? Yeah, if I had a right angle triangle, here's my angle theta. The longest side is called the hypotenuse. The side opposite the angle theta is over here called the opposite. And the side next to it, you bet, is the adjacent. So what's that lovely phrase? So, SOHCAHTOA. Yeah, so sine is defined as the length of the opposite divided by the length of the hypotenuse. I'm going to get lazy. I'm not going to write down the length of. I hope you understand. So cosine is just the length of the adjacent side divided by the hypotenuse. Tangent is the length of the opposite side over the adjacent. That's where you get the OA from TOA, or the ka, A adjacent over hypotenuse. So opposite over hypotenuse. So what are the two special triangles? Da, 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 da. Turn the page. So the first one actually is created if you draw a square with side length 1. If I asked you to cut this in half like a grilled cheese sandwich, you'll get a lovely right angle triangle. Since I told you these were side lengths of 1, if I cut this in half, these are 45 degrees. And hopefully you know from Pythagoras that the side length, or sorry, the hypotenuse over here will be 1 squared plus 1 squared. Take the square root, or just root 2. Why is this important? Well, if you look underneath, I've got here my triangle, 1, root 2, 45, 45, 90. And what's sine of 45? Well, let's just take this angle down here as our 45. Opposite would be 1 over hypotenuse, or root 2. By the way, for those of you who already done the chapter on radicals, that's chapter 5 of Math 11, you should know how to rationalize the denominator by multiplying both the top and the bottom by root 2 over root 2. So sometimes people write this as root 2 over 2. So this is good, or this is good, either or. Okay? I prefer the actual one on the right, the root 2 over 2, and you'll see why in a second. Cosine 45. Well, cos is just the adjacent, which is also 1 over root 2, or my preference, root 2 over 2. Tangent 45. Tangent is opposite over adjacent. That's 1 over 1, or of course just 1. So there you have it. Your special angles for 45 degrees. So where's the other one coming from? Well, it's the equilateral triangle I'm going to ask you to draw. So And I'm going to ask you to cut this in half down the middle. I asked you to do length of 2, so this is 2. This used to be 2. If I cut it down the middle, then half of course, of 2 is 1. And now how do we find this height? Hopefully you remember if I called this h. H squared plus 1 squared equals to 2 squared. And 2 is the hypotenuse. So h squared equals to, I think, 3, or h equals to root 3. Here's my 90. Where are my other angles? Since this is equilateral, this must be 60. And since I cut this in half, hello, 30. Half of 60 is 30. So, in this case, I will draw 1. The hypotenuse is 2. And the height is root 3. There's my 90. The base angle here is 60. The top one is 30. And now go ahead and find the ratios. And you should do this on your own. Sine 30. Here's 30 degrees. Opposite is 1. Hypotenuse is 2. Cos 30. The adjacent is next to it. Root 3. All over 2. Tangent 30. That's opposite 1 over root 3. And let's do the sine 60. So now we're looking at the angle here. Sine is the opposite, so that would be root 3 all over the hypotenuse of 2. Cos 60. Hello, adjacents over here. That's 1. Hypotenuse is still 2. Tangent 60. Opposite is 3. Hypotenuse is 1, or just root 3. Cool. Alright. So, you're going to have to know all these things, okay? Remember how I said to you I kind of like writing it as root 2 over 2 for sine 45? You're like, why? Well, like I said, you need to memorize these or understand them, okay? You can either recreate them every single time by drawing the two triangles, or take a look at this little trick. So I wouldn't say a trick, but just a nice little pattern. I love patterns. Let me do that just down here, because I didn't really leave you enough space. Sorry. I'm going to ask you to write down the sine, cosine, and tangent. I'm going to ask you to write 30 degrees, 45, and 60 at the top. And we're going to make a little chart. Now, let's see what goes in the chart. In the chart goes the ratio. So, for example, in this space here, sine of 30, we know the answer is 1/2. And in this space over here, sine 45, that's root 2 over 2. And sine 60, looking here, oh yes, root 3 over 2. Okay? You go ahead and complete the rest of this chart. Cos 30, root 3 over 2. Cos 45, root 2 over 2. Cos 60, 1 over 2. Stop right there. Do you see any patterns? If you say, hey, they all divide by 2, And if you say, hey, look, sine goes 1, root 2, root 3, And then cosine goes backwards, root 3, root 2, root 1, And if you want to do one more thing to make another pattern, I will just put a square root on top of the 1, because the square root of 1 is just 1. And that's why 45, I use root 2 over 2 and root 3 over 2. So the pattern is root 1, root 2, root 3 going up. And for cosine, it's root 3, root 2, root 1 coming down. Okay. How about tangent? Well, I don't memorize tangent, but I do understand that tangent 30 is 1 over root 3. And notice where those numbers come from. They come from the numerators of the sine and cosine ratio. So really, if I just take the numerator of the cosine and sine ratios here, root 2 over root 2, well, that's the same thing as 1. And lo and behold, what's tan 45? 1. And if I do the same thing with the 60 degrees, root 3 over 1, that's just root 3. And notice tangent 60 is just root 3. So, if you want to understand the patterns and produce this chart every single time, and that helps you out, then by all means go to it. Alright, last example here, number 5. Yes, I'm Asian, so I used to play piano, okay? I say I used to because I wasn't very good. and so I stopped in about grade 9. Should have finished my ARCT, should have went to become a piano teacher, could have made lots of big bucks, but oh well. That's life. You make your choices, you live with it. Anyways, I remember when I had the piano, there was a metronome that ticked back and forth to help me keep track of time. My piano teacher always said I played the instrument way too fast, so I'd go really slow at the beginning and I'd rush to the end. So the metronome helped me stay on beat. Now the pendulum arm of the metronome swings, and in this case it swings from an angle of 30 to 150 degrees, and these are angles in standard position. So you're thinking about what happens if I draw my coordinate axes. I guess what happens is I'm starting here at an angle of 30 degrees, and this thing swings, swing, all the way over here to 150 degrees. Okay? So it goes ticks, tocks, goes back and forth. And the length of the actual metronome, this piece here, is 20. So I have at least one measure. Okay? They're asking for the exact horizontal distance. The tip of the arm travels in one beat. So here's one beat, tick, tick, right? So the exact horizontal distance will be this distance here. So how can we find that? Well, I hope you can see that there are triangles involved, and perhaps using right triangles might help even more. Perhaps if we use this right angle triangle here, and this is just one way of doing it, that might help even further. Let me just quickly draw it larger here. So we know that this angle over here is 30. That's not good because that doesn't give me an angle in my triangle. But I hope you can see that this one here is 60 because we have to add to 90. And here's 20. Alright, so I've got a 60-degree angle. I've got the hypotenuse. I'm looking for the horizontal piece here. I'll call that X. 60, I've got this opposite side, hypotenuse. If you wrote down something like this, sine 60 equals to X over 20, I'm pretty stoked and happy that you got that. And I guess now to solve for X, I just bring the 20 to the other side. So 20 times sine 60 degrees equals to X. And you're like, oh, I need my calculator. And I'll say, no. Sine of 60 is what we call one of these special angles. No calculator is required because you look at your chart and sine 60 is just root 3 over 2. So this becomes 20 times root 3 divided by 2. 20 divided by 2 is just 10. So X is just 10 root 3. X is the horizontal distance of this triangle, but that's not the exact horizontal distance that the tip of the arm travels. That, of course, is double. Because there's 1, here's 2. So the horizontal distance is twice of the 10 root 3. 2 times 10, of course, is 20. So 20 root 3 centimeters. And there you have it. All right, go and try some questions on your own. We're done.